You know, the world can feel pretty random, right? But what if I told you there was a way to find patterns in all that chaos? That's exactly what we're diving into today. The statistical tools that help us predict the unpredictable, turning what looks like pure chance into calculated probability. I mean, just think about it from a business perspective. How many calls is the hotline going to get? How many defects are in that next batch? These questions aren't just theoretical. The answers have a real impact on staffing, on quality, on the bottom line. People in statistics tackle this stuff all the time, and we're going to look at two of the most powerful tools they use to get it done. Okay, so our first tool is something called the Poisson distribution. And its main gig, it's all about helping us count how many times something happens over a specific interval. And that interval could be time, distance, or even area. Yeah, the big thing to remember here is that Poisson's is all about counting stuff that happens within a certain boundary. Think about it like how many cars show up at a drive-thru in an hour, how many typos are on a page, or how many calls a help center gets. It's a way of putting a number on randomness. Now, hold on. You can't just whip this tool out for everything. It only works if a couple of key things are true. First, the chance of something happening has to be the same over any equal interval. And second, one event happening doesn't make another one more or less likely. A car arriving at 10:05 doesn't change the odds for a car arriving at 10:06. They have to be independent.
All right, enough theory. Let's see this thing in action, right? We'll kick things off with a classic waiting line problem to see how Poisson works in the real world.
Okay, so let's picture it. It's a busy morning at a bank's drive-thru. The manager's done their homework, looked at the data, and they know that on average, about 10 cars show up every 15 minutes. This average rate, that's our key starting point. So, okay, the manager knows the average is 10, but what are the odds that in the very next 15 minutes, only half that number, exactly 5 cars, decide to show up? This is a perfect job for our new tool. So how do we solve this? We use the Poisson formula, and I know it can look a little scary, but trust me, it's basically just a recipe. We take our average rate, which we call mu, that's 10, and our target number, x, which is 5. You just plug those numbers into the formula, and it spits out the exact probability. And when you run the numbers, what do you get? A 3.78% chance. Now, that might seem tiny, but for a manager trying to figure out staffing, that's a real, solid number they can actually work with for planning. And hey, here's the good news. You don't always have to break out the calculator. Statisticians have already made these awesome little cheat sheets, probability tables. All you do is find the column for your average rate, in our case that's 10, and then go down to the row for the number you're curious about, which is 5. And look at that, right there, 0.0378. Same answer, no math required. So Poisson isn't just for time, it works for distance too. It's super flexible. Let's switch gears. Imagine a brand new highway with an average of 2 major defects per mile. The question is, what are the chances we could find a perfect 3-mile stretch with 0 defects? Well, first things first, we got to adjust our average. If we've got 2 defects per mile, then over 3 miles we'd expect, well, an average of 6 defects, right? And the probability? It's just 0.25%, a quarter of 1%. That is incredibly low. Basically, finding a perfect 3-mile stretch, it's a total long shot. To flip that around, it means there's a 99.75% chance you're going to find at least 1 defect in that section. Okay, so everything we've talked about so far has been about independent events. But what happens when one thing does affect the next, when events are dependent? Well, for that, you need a totally different tool. We're moving from just counting events to selecting items from a specific limited group. And that second tool, our next gadget in the toolkit, is called the Hypergeometric distribution. And if there's one phrase you need to remember for this one, it's sampling without replacement. Think about it like drawing cards from a deck. Once you pull a card out, it's gone. You can't draw it again, and that changes the odds for the next card you pull. And that right there is the key difference. With Poisson, it's like the pool of things that can happen is basically endless. But with hypergeometric, we're dealing with a small, fixed group of things. And every single time we take one out, the probabilities for the next draw completely change. You know the drill. The best way to get a feel for this is to see it in action. So let's leave the highways and banks behind and head over to a factory floor for a little quality control. All right, here's the scenario. We've got a box. It has exactly 12 electric fuses. That's our finite population. We know exactly what's inside. 5 of them are defective, 7 of them are good. An inspector's going to pull 3 of them out at random to test them. So, The big question for the quality control team is this. Out of those 3 fuses they pull, what are the odds that precisely one of them comes from that group of 5 defective ones? So this is what we're starting with, a pool of 12 fuses, and we know exactly what's what, the good ones and the bad ones. This is the pool we're about to take our sample from. So we crunch the numbers, and what do we find? The probability of finding exactly one bad fuse is 47.73%. Wow, that's actually really high. It's almost a coin flip that the inspector's sample will turn up exactly one faulty part. And this is what sampling without replacement is all about. Let's say the inspector's first pick is a defective one. Bam, the whole game changes. Now there are only 11 fuses left in the box, and only 4 of them are bad. The odds for the next pick are totally different than they were a second ago. Okay, so knowing the odds for finding exactly one is cool, but what does an inspector really want to know? They probably want to know, what are the odds I find any bad fuses at all? In other words, what's the probability of finding at least one? And the answer is a whopping 84.09%. So how do we get that number? Well, instead of adding up the odds of finding 1 and 2 and 3 bad fuses, there's a clever shortcut. You figure out the probability of finding 0 bad fuses, which is about 16%, and then you just subtract that from 100%. This tells the inspector there's a really high chance their small sample is going to catch this problem. So we've looked at 2 totally different kinds of problems and 2 really powerful tools to solve them. But honestly, the real skill isn't just knowing the formulas. It's knowing which tool to pull out of the box for the right job. So let's break it down one last time. This is the main takeaway. You're going to reach for Poisson when you're counting things that happen independently over some interval where the probability doesn't change. Think arrivals, calls per hour. But you'll use hypergeometric when you're pulling from a small known group, and you're not putting things back, so the probability changes every time. Think quality control or even a hand of poker. You see, in the end, randomness isn't always as, well, random as it looks. With the right tools in your belt, you can actually start to measure it, predict it, and make way smarter decisions because of it. So the only question left for you is, what random thing in your life are you going to analyze first?